I hope you went through the lecture that I missed last week. Did you go through the lecture? Honest answer. Yeah, who did not go through the lecture? Okay, well, you have, you have, I'm gonna go through that very quickly just to remind you, but these are very important. This is a very important lecture. These are very important lectures. There's a big homework on them. It's perhaps the hardest homework of the entire course, one of the hardest ones. There's a lot of testing that you would need to do and numerical experiments in the homework. And also what's nice about this topic that we're covering now, I don't want you to lose sight of our objective. I'm also limping a little bit. I woke up with like a cramp in my calf. I'm like, what's going on? My wife was like, you're just getting old, just get out of bed, go take the kids to school. And so it is what it is. But these lectures, don't lose sight of why we're doing this. Remember, we're operating within the vicinity of linear systems of equations. We like linear systems of equations because they're linear, we can solve them. Later you will see nonlinear, they are harder to solve. But linear equations, anytime you can convert a problem into linear world, it's easier to solve, it's tractable, it's more understandable, it's generally not as costly as the original system. If you went through the lecture, you would have observed that we were dealing with a one-dimensional heat transfer problem. And I use that example because it's physical. It tries to anchor this course to reality. A lot of tools in this course, it can seem abstract and disconnected from reality. I want it to be connected with reality. So that's why I give this example. And also, it's an opportunity to see how large systems of equations do show up, okay? So actually, your TAs yesterday, Davin and Lillian, they were telling me that they're doing the two-dimensional version of this problem in heat transfer. So next year, you'll be doing that in your junior year. And they were very, very thankful for numerical methods. And if it wasn't for numerical methods, they wouldn't know how to solve it. And Davin is approving there. Anyway, so they're going to be useful for you for next year for sure. And they'll at least give you a more efficient perspective on how to solve the problem. So in the slides, in the lecture you probably watched on YouTube, I wanted to remind you of these two approximations that we learned about this approximation for the first derivative. And at the time, you always wondered, like, what the heck are we going to use that for? Well, this is an example of where you use an approximation to a derivative for. And specifically, in this case, we're going to use the approximation for the second derivative. This one was for the first derivative. This one is for the second derivative. It gives you the approximation at some point, xi, how it relates to two neighboring points. What is h? We'll figure that out in a minute. Okay? But the point is that there's an approximation for the second derivative. Again, right now you're not responsible for deriving these equations. I will give you these equations, okay? But you'll be responsible for putting them together in a matrix and solving them. Okay, and the problem set up, as I described, I think, on the Tuesday or whatever before the lecture I missed, there was a rod that's being heated, and there's a heat source in the middle that's heating the source. The rod or the spatula or whatever, the wall is anchored at two temperatures on both sides, and these hatched lines over here, bless you. And the temperature is known, it's fixed, it's a known quantity, so it is not a degree of freedom. When we say the word degree of freedom, we just simply mean an unknown. How many unknowns do you have, right? How many ways can you change the system that you are not fixed? The boundary conditions are fixed. The source term is also fixed, right? So in general, we would know, like this could be a fire or like a blow dryer, right, hair dryer or something, that you're adding heat or subtracting heat from the rod, so you know information about it. And that's represented by S of x. So S of x is a source that could no heating over here, and there's a lot of heating over there, and then no heating over here. Okay? So that's what we're looking at. And the governing equation for this problem is this relation between the second derivative and the source term. And what we are, a second derivative of the temperature. Why second derivative of the temperature? You'll study that in heat transfer, but it has to do with what we call the heat flux. How much heat energy is being transmitted, and the heat energy is proportional to the gradient of temperature, the derivative, and then the derivative of that gives you you learn about that in heat transfer. But that's why you end up with, so take this as a given, trust me on this one. And on the right-hand side, you have the source term that's influencing how the temperature is changing along the rod. If you took ODEs, you might be inclined to say, I want to solve this exactly. Maybe you can, maybe you cannot, depending on S of x. If S of x depends on temperature, which it doesn't here, but if it does, it makes it nonlinear. It makes the problem harder to solve. But you can generally maybe solve this analytically actually by hand. It's a complicated solution, but we're not going to do that by hand. There's also this coefficient k, this value k, there's 1 over k. K is what's called the heat transfer coefficient, and it's a property of materials. The higher the heat transfer coefficient, the more that the material can conduct heat. Okay? So a piece of metal, a piece of wood, right? And you put temperatures. Look, why are spatulas made of wood and you stick them in the hot water? Because they're not going to get hot as fast as a metal spatula that you put in boiling water. Why? Because metal has a higher propensity to transfer heat, which means it has a higher value for K. Okay? In the mathematics of it, that's what this means. Different materials have different heat conduction. That's why you put a gap or you put air in double glazed windows, right? Because air has a much lower heat transfer coefficient. So there's heat from the outside. The heat is trying to come into the house, but then, it meets air. And then the air is going to resist that heat transmission significantly. And then you have the second piece of glass on the other side, right? So, that's what you learn from heat transfer. Very simple idea. So K describes that process. Nothing is useful without dimensions and units. Typically, K is given in watts, which is joules per second. It's a heating rate. Per meter per Kelvin. So it's a function per degree Kelvin per temperature. And the source term is watts per cubic meter. So it's generating heat volumetrically. So for example, the sun produces about 1,400 watts per square meter. Okay, like just to put things in comparison, like if you pick a surface on Earth, you're standing in front of the sun, you're receiving about 1,400 watts per square meter. Okay. So if you didn't do it, go through the lecture. It takes about 1 hour to go through this explanation. I hope you went through that. I'll go through it real quickly again here. So the process would be to solve this numerically is first we have to define discrete points on which we're going to solve this problem, because we cannot solve it continuously. Continuously means you're solving it by hand. Okay, we're assuming we don't know the solution by hand. We want a generic solution to this numerically with computers. And with computers, because they're digital, we have to digitize the rod. And so we split it into a bunch of points. And we say that we're going to assign a variable at each one of those points, starting with T0 on the left all the way to however many points we want. I put 6 points here. So we're going from T0 to T5. But you could go to T million. You could put 1,000,000 points here. Okay, that's going to be the power of this problem. We're going to be able to scale it and add more and more points. What's the advantage of adding more points? More? Yes, more accuracy. Yep. So what's the difference between accuracy and precision? Accuracy, and what about precision? Be tighter. Yeah. Okay. Any other interpretations? I like to think of accuracy and precision as accuracy in general. You want to at least achieve accuracy before precision. Accuracy means truth. Okay, it means you're pointing to the truth. So I can tell you, there's a gas station that way. Like, yeah, that's right. Versus there's a gas station here. That's wrong. I could tell you, because I know there's a gas station there somewhere, right? That's not precise. I'm not telling you exactly where, but I'm pointing in the right direction. But if I tell you there's a gas station over there, if you take a right turn and then go left, climb 7 stairs, that's a lot of precision with no accuracy. So no amount of precision will make up for accuracy, for truth. So first you need to be accurate and then precise. Okay, so more points technically is going to get us more precision. Accuracy, just solving this problem even with 10 points, will get us some version of the truth, will point us in the right direction. Okay? But to get more precise, more close, clustered towards the center point, the bullseye, you need more, you put more points. Okay. So later you will learn how to convert a continuous differential equation into discrete algebraic systems of equations. So what I mean by that is I want to convert this ODE from a continuous derivative to linear equations. Right? Linear equations are algebraic. That's what we started with. We're solving algebraic equations. Okay. So and the process I described in the lecture on YouTube is, again, you don't need to master this now, but I want you to understand how I'm doing this. I take this second derivative, I approximate it with this approximation, so I convert the derivative to an algebraic relation between these points, the temperature points that I want to solve for. I don't know them. So for every point I have on the rod, I need one equation. Same number of points as there are, same number of equations as there are unknowns or as there are points, right? So that's what this accomplishes for you. At every point on this grid that I called, hopefully this is resonating with what you saw on YouTube, I can get an algebraic equation that relates the neighboring points to each other. Previously, when we began, we called these X, Y, Z, W, T, Q, or we call them concentration A, concentration B, concentration C. Here, we're calling them T1, T2, T3, T4, T5, T6. It's just a different variable name. The beautiful thing about this is that this equation, this formula, is the same at any one of those points. So it's not a different equation per point. It's the same equation at each point, but it relates different points to each other. So that's why we write it in terms of some arbitrary index I. This I could be 0.1, 0.2, 0.3, 0.4, 0.5, all the way to however many points you have. At the boundaries, you know the temperature, so there's no equation there. You already have that equation. You have T0 equal whatever is given to you, and T end is whatever is given to you. But everywhere in the middle, this is the equation. And so now you have one equation per unknown, and there you go. You've built your system of equations. So for point 1, you just take I equal 1 and put it here. You get T2 minus 2T1 plus T0 equal minus delta x squared, the source term evaluated at x1, the location 1, over k. So you get that equation for point 2, for point 3. So it's the same thing. It's the same equation over and over again, except it's relating different points to each other. Now you can see how, hopefully, that this is a linear system of equations with unknowns going from T1 to Tn minus 1. Of course, I'm including T0 and Tn. We know the equations for those, so I'm going to include them in the system as well. Okay. Now and then in the lecture, I asked the question, okay, so what is S of x1, S of x2? That's simply the source term evaluated, because S is a function of location on the rod, right? It changes based on where you are on the rod. And so the same way you assign temperature values, you can assign positions on the rod. And those are easy to calculate, right? Because you say, okay, I want 5 points or 10 points or 100 points on this rod. You take L divided by the number of points or intervals, and you can get the location of all of these coordinates. So for example, also hopefully if you went through the lecture, so if L is equal to 1, the length of the rod, and you want 5 intervals, So count with me, 1, 2. So the interval is between 2 points, right? So that's the interval. But the points, we have 6 points here, or 5 intervals. So if L is subdivided into 5 intervals, then the spacing is 1 over 5 intervals, or L over 5, right? And then x0 is 0, x1 is delta x, x2 is x1 plus delta x. So you keep building that, etc., all the way to the end. Now, luckily in Python, linspace will do that for us. Because we go tell linspace, take the rod from 0 to 1 or 0 to 2, and put 51 points in the middle. It does that automatically for you. So you have your coordinates on the rod real quickly, okay? All right, and then it's the same way that we can create coordinates for the rod, we can evaluate the source term at each one of those points. So now you're not thinking continuously, you're only thinking at the points that you chose to evaluate the temperature at. You don't have a value of temperature between any 2 points, because you're not solving it there. You only have the value that you will solve at those points. Okay? So same way, you have x1, x2, x3. You can evaluate s of x1, s of x2. And obviously, you don't do that as a loop, because your x values are going to be a linspace. And then you apply the source term directly on that linspace. It will give you the value of the source term at each point, right? So for example, if s is e to the minus x squared, which is what we're going to do in this problem, it's like a Gaussian distribution for heat. So no heat at the edges and some heat in the middle maybe. This is what it would look like. It's just simply evaluating the source term at all of those points. So always try to tie it back to your equation. So in the end, for like say 5 points, we have one equation at each of the blue points. For point 0, you have T0 equal TL that's given to you. Now I like to include that in the system of equations. Also, this is a silly case, T0 equal 5 or 100, right? But I like to include it in the system of equations because when I solve the system of equations, it's going to give me the solution for the temperature. I also want to plot it at the endpoints. So I want the endpoints to be included in the solution. So I make sure everything looks nice and clean, okay? That's all there is to it. For point 1, you have the equation at point 1. It's related to T0. You keep T0 here. Although it's known, but you're putting that on the right-hand side, you're treating T0 as an unknown. So that's fine. The system is smart. It will find the solution T0 equal TL for that point 0. And then for point 1, you have this equation. For point 2, you have the equation at point 2, and so on and so forth. And then I ask you to write the equation for point 3, 4. I hope you do that. Again, if you didn't, you're going to miss out a lot. You're going to be in a lot of trouble in homework 3. In your homework 4, I guess, if you didn't do this exercise from that lecture, please, 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 I urge you to do it. You do it by hand. Otherwise, you're going to be spending the last few hours of your homework trying to scramble for help sessions and questions. So try to do that. Go and do that with the lecture. If you have questions, ask us early on. Okay? You should be able to derive this system. Now, this is done for just these 6 points, so T0, and then the last point is known. Okay, T5 is equal the temperature on the right. Okay, so when you look at this, there's nothing dangerous or scary about this. This is a blind system of linear equations. How do I know it's linear? Ash.
Because S is the only thing that we're seeing, and it's not, doesn't have a power to it or anything like that.
S is a known number. S is not even a variable. So what are the unknowns in these equations? Michaela. And T3 and T4 and T5, right? All the T's. Those are our unknowns, right? How do they show up? And smiling is not an answer. They don't show up smiling. I mean, I hope they show up smiling, but they show up. There's one of two answers, either linearly or non-linearly. Yeah, so before we get there, yeah. So how, yes? Yeah. Yeah, the variables, they show up linearly. They're not There's no cosine tq, t3, or t3 to the power 4. There's none of that. They're just showing up linearly in each one of those equations. And when you look at it, if each equation is linear in the unknowns, then the entire system is linear in the unknowns. And what do we do with linear systems? We write it in matrix form, as your colleague suggested, okay? Now, before you worry about this, you're not going to derive these now. You will derive them later at the end of the semester, and you'll be responsible for that. But now, right now, I will give you this formula. I will tell you that the equation at each point is ti minus 1 plus 4ti. I'll give you that formula. And then it's up to you to build the system of equations, okay? I'll give you the formula, all right? You're not responsible for deriving the formula. So then, when you see this, you have to write, again, you have to do this exercise. So if we did the lecture last Thursday, you would be doing these activities. I would not let you go until this is anchored in your mind. So you have to know how to do this. Otherwise, trust me, I've taught over 1,000 students on this. If you can't master this, you're going to be in trouble for a lot of the material that's going to come. Okay, so do it now. Do it now. It's going to get exponentially more complicated. Okay? You do it now with 5 points, it's a blessing. Do it now. You do it for 5 points, you can do it for any number of points. Okay? Now, this is what the system would look like. I write my vector of unknowns from t0 to t5. And then I build my matrix. My first equation, remember, in the matrix, the rows, they represent the equation. My first equation is simply 1 times t0 equal tl, plus 0 times everything else, right? My second equation at point 1 is going to be t0 minus 2t1 plus t2. So that's t0 minus 2t1 plus t2 equal minus delta x squared times s1 over k, and so on. Going from this to that. Now, you see why the beauty of writing it in matrix form. You see a structure emerge. You have a main diagonal that's non-zero, an upper diagonal that's non-zero, and lower diagonal that's non-zero, and everywhere else is zeros. So that's an example of a tridiagonal system. If you remember, I told you that these show up in heat and mass transfer problems. So next year, when you're doing heat and mass transfer, you're going to be dealing with exactly these systems. Okay, and you'll be solving this exact same problem. You'll be doing it in 2 dimensions, which is going to get harder, but you just have more unknowns in that case. You'll just have more unknowns. Okay? Now, we know how to solve this actually right now, so that's what we're going to do next. We're going to take this system and program it, but guess what? We're going to program it not for 5 points, we're going to do it for 1,000 points or 100,000 points. Does the matrix change? Does the look of the matrix change if we add more points? Yeah, it just increases in size, right? You just have more minus 2s everywhere, right? The upper diagonal is always 1s except the first guy here. The lower diagonal is all 1s except the last guy. You're just adding more points in the middle. It's like taking that matrix and just expanding it. You have more and more and more points in it. Okay. So what you should take from this is how the matrix looks like. And in general, if you were to subdivide the matrix into n points or n minus 1 intervals, the matrix would look the same. You have minus 2s everywhere here except the first and last entry. On the lower diagonal, you have 1s except the last one is 0. On the upper diagonal, you have 1s except the first one is 0. Your vector of unknowns is still the same, t0 all the way to tn or tn minus 1, whatever you're going to call it. And then on the right-hand side, you have left temperature, right temperature, and in between, you always have delta x squared times si over k. Okay, now, this will be built in one line as a vector application on the Lin space. And these guys, we're going to look at how we can build this matrix very efficiently. So now, what kind of matrix this is? This is called a tridiagonal matrix because only 3 diagonals are non-zero and everything else is 0. Okay? And those 3 diagonals happen to be nested close to each other. The main diagonal, first upper and first lower, right? And Then I have a bunch of activities here. Again, go through that lecture. So I want to get to coding it actually. All right. This is also a sparse matrix. Okay, so this is going to be important. I want to make sure that I cover this. So this is not only a tridiagonal matrix, and the size of the matrix is, remember, you have n points or whatever, n entries. Okay. So n equations and n unknowns, but the matrix has n squared entries in it because you have n rows times n columns. So you have n squared entries in the matrix. Why is that important? Because I'm worried about space complexity. If I were to store this matrix and most of it is zeros, each zero is going to cost me the same amount of storage as a non-zero number. And then you ask yourself, do I really need those zeros or not? So this actually allows us to think about sparse matrices again. So I mentioned earlier that iterative solvers are going to be very efficient on sparse matrices. And we will use this example to actually prove that or demonstrate it. So this is not only a tridiagonal matrix, it's also a sparse matrix. Now, we formally define what a sparse matrix is. First, we define sparsity, or the sparsity of a matrix is defined as the number of zero-valued entries. So how many entries do you have in the matrix that are zeros, okay, over the total number of entries of a matrix? Okay? So you're just counting the number of zeros over the total number of entries in the matrix. Okay? So typically, this is an n squared number of entries, so you know the total number. But then the trick is figuring out how you count the number of zeros. And then you say a matrix is sparse if its sparsity is 50% or more. So in other words, if the matrix has a sparsity of 50% or higher, or more than half the entries are zero, then the matrix is sparse. So take a matrix, all of it, count the number of zeros. If the number of zeros is 50% of the total number of entries in the matrix, then the matrix is sparse by definition. Okay, that's the definition. Okay? So in other words, if more than 50% of the entries in a matrix are zero, then the matrix is sparse. Okay? All right, so I have a couple of activities here that would have been done. I mean, it was a great lecture, last lecture. So maybe we do this activity right now, actually, just to get you to be a little bit more engaged with this. So for a general tridiagonal n by n matrix, okay, so we have n by n matrix, total entries is n squared, agreed? And I have three, the first main diagonal, the first upper, the first lower, are non-zero. Forget about the zero that's in there. Assume that those three diagonals in general are all non-zero. Okay? So now I want you to develop a formula for the sparsity of a tridiagonal matrix. Okay? So develop a formula for the sparsity. Remember, the sparsity is the ratio of zero-valued entries divided by the total number of entries. So you already have the total number of entries. It's n squared. Now go figure out how many zeros you have in a tridiagonal matrix. So this is a great exam question. I'll give you a matrix structure, and I tell you, figure out, give me a formula for the sparsity, or get the sparsity of a given matrix. Okay? Put your names out, please. So I'm still trying to remember everyone's name. Hopefully by the end of the semester, I know half of you. So the trick is counting the number of zeros. But you can get the number of zeros, you know the total number, but you also know the number of non-zeros. It's easier to count the non-zeros and deduce the number of zeros from that, right? So count the number of non-zeros, which are the three diagonals. Remember, only the three diagonals are non-zero. Yeah, so the sparsity is the number of zeros over the total number of entries. So to count the number of zeros, you know the number of non-zeros, so maybe you count that first and deduce the number of zeros from that, okay?
So the formula is for how many non-zeros there are? How to
Yeah, so the formula is to get the formula for the sparsity of a tridiagonal matrix. So number of non-zeros in a tridiagonal matrix over the total number of entries. Yeah, yeah, yeah. I'm trying not to be, maybe I should wear my mask. I don't know, it's been like a week, but all right. It makes everyone feel better. You too?
Professional development, they're like, did you watch the video? And I went, what? Tomorrow. And there's no work. Does that look right?
How did you get those numbers from?
What? From here.
Oh. So what did you do?
The matrix is n squared total, and then I subtracted.
So you got n squared minus,
n minus 1, and that diagonal's n minus 1.
Okay, so you did n squared, which is total minus n minus n minus 1 minus n minus 1.
Yeah.
Okay.
Yeah. Does
Okay.
that work?
Yeah, you're just like, it took me a minute to.
Oh.
But show your steps, Gretchen. Yeah,
Okay,
show your
okay,
steps,
okay.
okay? It's much easier than you think. How many entries are on the main diagonal? How many entries on the main diagonal? How many entries on the main diagonal? N. How many entries on the first upper? How many entries on the lower diagonal? Use that to get the number of zeros. What?
Why be minus 1?
No. What?
Why is it minus 1?
On the first upper? Because you have one equation less on the diagonal, right? The last entry on the upper right corner is one entry, right? Then 2 entries, and then 3 entries all the way to n entries, right? So, okay. Need more time? Yeah, I'll come and help you. Sorry, did you need help?
I think I got it. I just am like trying to like finish.
Okay.
So we just add the diagonals, like the upper, middle, and lower. We just add them together to get all the zero ones.
Yes. Yep. Those are the only non-zero. Yep. And then from that, deduce the zero. There. Yep. Don't look at my slides. The answer is in my slides. Don't look there. Yes, Gretchen. Yeah, so if you count the number of non-zeros, so main diagonal, first upper and first lower, right? Subtract that from n squared, you get the zeros. Right? So how many entries what are the non-zeros? Main diagonal, first upper, first lower, right? How many entries on the first diagonal? How many entries on the main, on the first lower, first upper? You guys can work together. Oh, your group is not here today, huh? Okay. Okay, who wants to show us the way? You've been volunteered, so that disqualifies you. Do you want to show us the way? What you did?
Yeah, I mean, so I'm taking the total number of entries, so n squared, and then I'm subtracting the diagonals, so I know that the middle one is n, the upper is n minus 1, the lower is n minus 1.
n squared. Okay. All right. Who else got that? Okay. Okay. Good. Okay. There's so many zero diagonals. Oh, you had a question?
So could we also calculate, maybe this is just like a shot in the dark, but could we calculate the zeros just by almost finding like the area of that triangle? Right?
Sure, maybe, yeah. But you got to count it right. This is much simpler, but yeah, you can do it geometrically, I think. Try it. Okay, so here's what we're going to do. Matrix size, total entries is n squared. Okay, we agree with that. We've seen that. Main diagonal has n entries. First upper has n minus 1. First lower, first upper and first lower have n minus 1 entries. So the total number of non-zero entries, so the main, first upper, first lower, you just add the number of entries, n plus n minus 1, n minus 1, you get 3n minus 2. So that gives you the number of non-zero entries. Therefore, and everything else is 0, so the number of zeros is simply the total number of entries minus the number of non-zero entries. Total number of entries is n squared, and the number of non-zeros is 3n minus 2, which we just calculated. You divide that by n squared, so that gives you the sparsity of the matrix. Okay, that's the formula. Okay, so now for n equal 100, only 100 points. Only, I have to stress that because, like, if you come and tell me you solve the heat transfer problem with 100 points, I'm gonna giggle because that's nothing, not even close to precision that I desire. Okay, yet at only 100 points, your sparsity is 97%. So 97% of the entries in the matrix are 0. Now that has incredible implications on storage, which we'll talk about later. But keep that in mind. Sparse matrices can be very expensive, especially that you really don't need to store the zeros. They're just doing nothing. So why store them at all? Okay, so there are techniques that would allow you to store this matrix very efficiently without storing the zeros. We're going to get back to that point later. All right, so we're going to Pythonify this now. And I don't know if do you remember anything from the lecture on YouTube? Okay, so do you remember how we built the matrix on YouTube? Okay, so if that's the case, I can go through this a little faster. So obviously, and if you remember, I said one time, for small matrices, you just enter them by hand. Like it's 5 by 5, 7 by 7, 10 by 10, just put them by hand in a nested list, and you're good to go. Don't worry about that. But for something like this, where I'm going to ask you, okay, do it for 10 points, do it for 100 points, do it for 10,000 points. You're not going to enter those values by hand, especially that they are the same. There's -2 everywhere. There's 1 everywhere on the first upper, on the lower diagonal, right? So it would be cool if we have a mechanism that could automate that process. Build this matrix for 100 points, or 200 points, or 700 points. Automatically do that. We have all the information we need because the main diagonal, it's always -2 except the first and last entry. The first upper is always 1 except the first entry is 0. And the lower diagonal, first lower, is always 1 except 0. I know how big they are. So it'd be really cool if we could only build the diagonals, which is pretty easy, mp.1s, right? For all of these diagonals, mp.1s of size n or n minus 1, and adjust the edges, a little bit, the first, last entry, and then somehow put them together into what looks like a matrix. So we have the facility. That turns out the people who built Python, apparently I made that joke last year, so I'm going to use it again. So maybe they took this course, I said, so they're learning about efficiency and making this nice. So there's facility in Python that allows you to do exactly that. Okay, so what the plan is going to be is we're going to take 1D arrays for the non-zero diagonals, like numpy.1s, okay? and fix the edges on those arrays and then put them together in a matrix. So step one is we build the 1D arrays for the non-zero diagonals. So np.ones, it creates a vector or an array of size n that contains the value 1 for each entry. So np.ones is 3. You create an array that has 1, 1, 1, 3 times. np.ones 5. You create an array that contains 1, 5 times. Okay? np.ones of size n, whatever n is, can create an array of ones of size n. Okay? Now, to create non-trivial values, like -2, how do I do the -2 in the middle? Simply do -2 times np.ones. Okay? So my main diagonal is D. -2 times np.ones of size whatever is going to give me -2 everywhere. Very simple. Okay? Now, how do you fix the endpoints, the first and last endpoint? You simply access those values and manually set them. It's a very easy thing to ask. So now, assume I'm working on the main diagonal. First, I create a main diagonal filled with -2. So it's all -2. So now think this is going to be on the main diagonal. I still need to fix the first value and the last value. They need to be 1. So now D at 0, I access that first value, and I set it equal to 1. So it changes the first value. How do I access the last one? I use circular indexing. I go from the back. D -1, the last entry needs to be 1. And now I have what looks like my main diagonal. And you can scale this. Instead of 5, you can put 1,000,000 here. It will just work. Nothing will change. Because always D0 and D-1 are always 1. And this guy is going to give you the right size array. Okay? And we'll do this in the code together in a minute. Now, step 2 is to combine these 1D arrays to build the full coefficient matrix. Our goal is to solve this system of equations for the temperature. We haven't done that yet. So we're just building the coefficient matrix, and we know numpy.linalgebra.solve takes a coefficient matrix on the right-hand side. So we need a full coefficient matrix. We haven't done that yet. We just created the diagonals now. The main diagonal, maybe the upper, the lower. So now we need to take the upper and the lower diagonal and the main diagonal and combine them together to build that full matrix. Again, Python people are smart. They made that facility for us. And the function called, the routine is called np.diag. So it comes from NumPy. And what it does, it creates a dense matrix, so stores everything. But it takes, np.diag takes a vector, a 1D array, so like the ones we just created, and places it on the kth diagonal on a matrix. Okay? How does it deduce the size? It figures that out by itself, because if I'm placing the main diagonal, if I'm placing 5 points on the main diagonal, it automatically knows that the array is going to be, the matrix is going to be 5 by 5, right? Because the main diagonal has n equal 5. If I'm placing on the first upper diagonal 5 entries, then the matrix will be 6 by 6, right? It knows that automatically internally, okay? So V is that 1D array that we just created. It's a NumPy array, so it contains any one of those diagonals. K is the location of the diagonal on the matrix. How do we count diagonals on the matrix? It's an arbitrary thing. We say the main diagonal always counts as 0. That's our reference diagonal. It splits the matrix in half. So that's going to be our 0 index for the diagonal. So the 0th diagonal, according to this functionality, is the main diagonal. So k equals 0, we put V on the main diagonal. If you go up, k equal 1 is the first upper, k equal 2 is the second upper, and so on. K equal -1 is the first lower, k equal -2 is the second lower, and so on. Okay? So that main diagonal splits the indexing right in the middle. It is assigned an index 0. And first upper is 1, first lower is -1, and so on. So what we are going to do here, we're going to create the main diagonal, and place it at, and use np.diag and place it at k equals 0. And we're going to do the same for the first upper, place it at k equal 1, and first lower, place it at k equals 0. But then what do we do with that? Well, np.diag is just a matrix. If we add them to each other, it's just like matrix addition, and they're going to add. So all we do is add them to each other to create the full dense matrix. Okay? So I have a warning here, though, that this np.diag is still storing a dense representation of the sparse matrix. So it's still storing the zeros. Okay? And that's okay. For the scale of our problems, that's fine. These are one-dimensional problems. There's notes at the end of the slides that I don't cover in this class, but for your own future, on how to store matrices in a sparse way. That saves a lot on storage. Okay? But we're not going to worry about that right now. But just be warned that np.diag is convenient, nice and easy, allows us to solve the problem. It's very effective for the scale of problems we're solving here. Okay? So then the full picture emerges in that this entire matrix can be written in a few lines of code. It's incredible. Where we started with the equations, matrix representation, and just a few lines of code. And all you need to change here is n, this value. Choose a value for the number of equations. You create the main diagonal, minus 2 times 1s of size n. So that's all minus 2s. Fix the first and last entry to 1. The upper diagonal, I call it u, and it's a numpy.1s of size n minus 1. Okay? And then I fix the first entry to 0, as shown up in the matrix. Same for the lower. It's all 1s except the last entry. And then I combine them together with the diag routine. And I build the matrix A. So A, I'm going to take my main diagonal, place it at diag at location 0. And to that, I'm going to add the upper diagonal placed at 1 and the lower diagonal placed at negative 1. Each one of those is a matrix by itself. You add them together, it adds each entry and results in the full dense matrix. Okay? So now the rubber hits the road, and we're going to do this together in class for the rest of the lecture. Hopefully, we'll finish this problem entirely. All right? Let's get your Jupyter notebooks up and running. And for this problem, we're going to play with the parameters. So I haven't defined any parameters here. So we're going to set them as we build this problem together. For the source term, I'm choosing this function. This is the famous bell curve. And it's nice because I only want heating here or here and 0 everywhere, right? No heating everywhere else. So I want to focus the heating at one spot. So I use this bell curve or the Gaussian function, okay? And we'll talk about that in statistics next semester. But this is this, you hear the bell curve distribution or the Gaussian distribution. This is what it is. The parameters here, they just scale that function. And I'll explain when we put it in the code. So essentially, this coefficient alpha tells us how big that function is. Is it going to heat 10 to the 1,000 watts per cubic meter or 1,000,000 watts per cubic meter? A tells you where the peak is going to be located. Are we going to locate this at 1/3 of the way, half of the way, or 2/3 of the way, whatever you want it? And sigma is what's called the standard deviation. Tells you how wide that bell curve is. Okay? So are you going to heat only at a few points, or are you going to heat like this or like that, right? So best way to do it is to print it out or plot it, plot it out. Okay? If you can come up with a nice slogan for me, like the equivalent of when in doubt, print it out, something for plotting, I would be very appreciative, okay, for you for that. ChatGPT couldn't even do it for me, so. Okay. All right, let's grab a Jupyter notebook, Python 3, window. All right. So let's import our boilerplate. Import numpy as np. Import matplotlib.pyplot as plt. And then we do our magic. Just going to copy that here. Matplotlib inline. You don't need that, but I always put it. Okay. And again, I'm being a bad example here because I can afford that luxury. You need to put your name, explain what you're doing, okay, be professional about it. If I were to do that here, we would never finish our lectures, okay? I'm more interested in teaching you the material than worrying about showing you, making sure I write the report cleanly, but you are expected to write it cleanly. It needs to be a clean report. As of homework 3 onwards, no grace for, non-markdown stuff, etc. You have to get it right. If you're confused, ask us. Okay? If you're confused, like whether this counts as a good presentation or not, just ask us before you submit your reports. Okay, so let's define some parameters for the problem. So let's say L is 1 meter. So that's meter length of rod. And number of grid points, that's going to be the critical item that you will change, plus the properties of the heat transfer material. But let's say, N is 100 points. So number of points, or in other words, N minus 1 intervals. So I choose to define the number of points rather than the intervals. It's up to you. Okay? The spacing is length over number of intervals, not number of points. So there's always one more point than there are intervals. 5 intervals, you get 6 points. 10 intervals, you have 11 points. Okay? You can choose to define the number of intervals or number of points. They're only going to be different by 1. At large scale, your answers are not going to be different. But just to be clear about that. And then dx, because I'm going to need that dx value where? When I'm computing the right-hand sides. Okay, so let me move this here. You get to see how my slides look like. Okay, so right here on the right-hand side, I have delta x squared, right? So I need delta x. So dx is simply L over n minus 1, number of intervals, right? Now, coordinates define the coordinates or the abscissae, if you want, on the rod along the rod. So this is the location. X is simply mp.lin space going from 0 to L. So the rod starts at x equals 0, ends at x equal L. And I need n points. So remember, lin space thinks in terms of points, not intervals. And if you're in doubt, print it out. Now, don't print it for 100 points, because if you print x here, you're not going to be able to read anything, right? Do it maybe for 5 points, right? Oh, for 5 points, 1, 2, 3, 4, 5 points. Okay, so 4 intervals. We start at 0 and end at 1. This is correct. This is perfect. Okay, so we go back to 100 and comment this guy out. All right. Okay. Bellissimo. All right, so let's do the source term. Let's define the source term. Def source. And I'm just going to make the source term a function of x only. I know we chose a source term that depends on alpha, a, and sigma, and x. I'm just going to make it a function of x and hard code alpha, a, and sigma. You can pass them as arguments if you want. I don't care. That's your code. Okay? And then gives you more flexibility to change parameters. All right? But sometimes when I'm doing like a rough calculation or back of the envelope, back of the notebook calculation, right? Back of the notebook calculation, I just kind of hard code some of the numbers just to get, because I'm anxious to get an answer. Okay? That's a good one. Back of the notebook calculation. Back of the notebook. Yes. Nobody laughs at my jokes anymore. It's like they're so outdated now. Hey, it's very hard for non-native English speakers to make jokes and even pun jokes in English. So when you ask any immigrant, they'll tell you, like, once they hit the pun joke mastery, then they've mastered, like, the language. That's a big deal. Seriously, like, ask your non-English, native English speaker friends, and they'll tell you, like, if they can make a pun joke, and they're so proud of it, be like the silliest joke and, like, cringe-worthy joke, but, like, we're so proud of it, so, you know. Any laughter would be appreciated. All right, so no worries. All right, so let's define for the source term. So we have alpha. So you can write this as alpha is equal to whatever. I'm going to use 1e to the 6. Or you can also type in Greek letters in Jupyter. If I haven't shown, did I show you Greek letters? In Jupyter? Yes? No? Yeah? Okay. So put \alpha and then press tab. It converts it to a Greek letter. Okay? That sometimes can be annoying because you're like putting Greek letters in the thing and copying it doesn't copy it nicely, right? So, you know, maybe spell it out as alpha if you want. But here we want 1e to the 6 for the amplitude. And I'm just kind of making up these numbers. Sigma, and we'll play with these numbers in a minute just to show you what they mean, 0.1. And A is L over 2. So I'm putting the source in the middle. I said A tells you where the peak is going to be. Now suppose you don't know what alpha, sigma, and A do. What would you do? I give you this function. I tell you, describe what alpha, sigma, and A do. You just experiment with it. You fix 2 parameters and vary the third one. Then you fix the other 2 and vary the second one. You fix the other 2 and vary the third, and then you can identify how each one affects your source term. Let's do just that. Okay? And then we're going to return np dot. So we're going to return alpha. So annoying to type, times np.exponential minus x minus a squared over sigma squared. So you remember this was my formula, e to the minus x minus a over sigma squared. So e to the minus x minus a squared over sigma squared. Okay, however you want to write that. Okay. So when in doubt, plot it out or something. Okay, so let's plot it. We already have the abscissa, right? And the source term is a function of x, so let's just plot it as a function of x, or along the rod. So what do we do? plt.plot. On the x-axis, I want to put the x location on the rod, and on the y-axis, I want to put the source term as a function of x. And let's add a grid. Okay. It does something. Well, at least, look, this is interesting. You already have an idea of what alpha does. At x in the middle, 0.5, you get that 1 to the 6. Right? So if I change that to 1 to the 4, it's just going to change it to 10,000, 10 to the 4, right? Not 1 to the 4, 10 to the 4th, right? So alpha controls the amplitude, the maximum, the peak amplitude of this function. Now, what's nice about this function, like I said, is I want concentrated heating in one spot. So that's why I chose it. It's 0 heating everywhere, and then it peaks very quickly to 10 to the 6, and then comes down very quickly and goes to 0. Okay? The value is 0 at the ends, right? Okay, so how do A and sigma affect that curve? So let's change A first. Let's go A equal L over 3. If you do A equal L over 3, it shifts it to the left, almost 1/3 along the way of the rod. Okay? If you go 2L over 3, for example, it's going to shift it to the right. So A is really telling you where you're at, where the heating is occurring along the rod. Very simply. Now sigma, I claim that that has to do with how widespread that function is. So let's try it. Let's put a very small sigma, 0.01 or 0.001. Look at that. It makes it such a very concentrated peak at like a few points only. Okay? Or you can make sigma bigger. Go to 0.5, let's say. If sigma is bigger, it's going to cover the entire rod. It's a very wide function. You will learn in statistics that that's the standard, has to do with the standard deviation, how wide spread the curve is. Okay? So that's why I chose somewhere like 0.01, sorry, 0.1, somewhere kind of reasonable in terms of how wide that heating is occurring. Is it too concentrated or is it spread throughout the rod? Okay, very good. So now we start defining the properties for the solution. So let's say T left, if we go back to our system of equations, right, we're trying to solve this guy here, this system, right? So I want to build the right-hand side, and I'm going to build the diagonals, main, first upper, first lower. I'm going to start by defining T left and T right. So those are the temperatures, the fixed temperatures at the endpoints. So let's say T left is equal to 300 and T right is equal to 500. So temperature in Kelvin. You know, Lord Kelvin, after whom the temperature scale is named, he had a famous quote. He said, "Machines heavier than air will never fly." You believe how wrong he was? Machines heavier than air cannot fly. And so no one is infallible. Okay? There's no authorities in science, there's only experts. And even worse than knowledge is the illusion of knowledge, that you think you know so much about something whereas you know nothing. Okay? Humility goes a very long way, but not to the point that you can't do anything, right? So you have to make decisions, but with a humility, right? With a sense of uncertainty about not knowing everything in the world. I had that quote in my dissertation from Kelvin, like, "Machines heavier than air can never fly," Lord Kelvin. So anyway, that wasn't his real name, actually. This is like a nickname or something. I forgot his real name. Okay. K is 400 watt per square meter per Kelvin, whatever the units are, okay? All right, so those are some of the properties we need, because now I have everything I need to build the right-hand side, which is great. I have delta X, I have S already computed, I have TL, T right, and K, so we got everything on the right-hand side. Let's start building the coefficient matrix. Let's build the coef matrix. Start with the lower diagonal. So the lower diagonal is a bunch of ones, all ones, except the last entry is 0. How many entries do we have in total? N minus 1 entries, because we already decided N is the number of points, number of equations, so that's already set. Okay, so I can use that to build the lower diagonal. So lower diagonal, I'm going to call it LD, very creative name, np.1s, n minus 1. Okay? So if you're in doubt, print it out. Print LD. It's just ones. You want to count them? There should be 99 of them. 1, 2, 3, 4, 5, 6, 7, 8, 99. Okay? I did it very fast at the speed of light, so you didn't see me. If you haven't seen the movie K-Pax, have you seen the movie K-Pax? Check it out. Yeah, pretty nice. It's a sad story, but Kevin Spacey in it talks about, like, he pretends that he can travel at the speed of light, and he stands in front of. I don't want to ruin the story for you, but like he's in a hospital. and his therapist is like really impressed with his knowledge of physics and astronomy. And I love astronomy, so I've done so any movie that has any slight discussion on astronomy or space, I will watch it for sure. And so he's talking about these planets and planetary alignments and stars. And the therapist and he tells him, I'm from another planet. I'm from planet K-Pax. Pretends to be, he's from planet K-Pax. And then he stands and he brings his physicist colleague, and the colleague starts asking him questions about relativity, about travel through space, wormholes and stuff. And Kevin Spacey is answering every question. And he tells him, in the end, I can also travel at the speed of light. And he stands there and he's just like, goodbye, hello. and there's no way for the physicist to verify that he actually didn't travel at the speed of light, right? Because he's like, goodbye, hello. So anyway, that's what I did there. I counted them at the speed of light, so you didn't see me. But watch that movie. It's called K-Pax. Okay, print lower diagonal. So we did that. All right, so we need to fix the lower diagonal. Okay, we need to fix the lower diagonal. This last entry needs to be 0. So we're going to go LD minus 1 is equal to 0. Okay, and now if I print it, again, you see 0 at the end. So now this whole thing is going to be flattened into a diagonal in the matrix at the end, okay? Great. So we don't need this anymore. Now the main diagonal, MD, is mostly minus 2s. So we're going to start by making an MP.1s of size n, all containing minus 2s. So it's going to be minus 2 times NP.1s of size n. Okay, and again, if you're in doubt, print it out. It's all minus 2. Okay, except the first entry is 1, and the last entry is also 1. Okay, print MD. Indeed, I got 1 for the first entry and 1 for the last entry. Okay, I want to go to maybe 5 points first, just to be able to visualize this a little bit better. Okay. So that's what the main diagonal looks like right now. 1, minus 2, minus 2, minus 2, 1. And then finally, the upper diagonal is also MP.1s of size n minus 1. But for the upper diagonal, the first entry is 0. Right? For the upper diagonal, the first entry is 0. Everywhere else, it's 1. So I can do the same. Print upper diagonal. And gives me 0, 1, 1, 1. Okay? So I'm capturing this upper diagonal here as a one-dimensional array. Okay. Almost there. Now build the full coefficient matrix. We're going to say A is MP.diag. We're going to place the lower diagonal at minus 1 plus the main diagonal at 0. So MD at 0 plus the upper diagonal at k equal 1. Okay? So what do you think is going to happen if we print A? It's going to look like a beautiful matrix like we expect it to be. Isn't that incredible? Python does that, all of that for us behind the scenes. It fills everywhere else with zeros. My main diagonal is 1, minus 2, minus 2, minus 2, 1. First lower is 1, 1, 1, 0, as expected. First upper, 0, 1, 1, 1. And that is a full coefficient matrix. Awesome. Okay? All right, what else do we need? The right-hand side. We're almost there. So build the right-hand side. Okay, so let's build the right-hand side. On the right-hand side, we have minus delta x squared times s at xi over k. So we already have s as s at xi because it's simply that source routine that we built, the source function, evaluated at the x at whatever x value, right? So if you're not convinced of that, let's go back here. Okay. Source at x is simply an array containing values at x0, x1, x2, x3, and so on. So this is S at x0, S at x1, S at x2, S at x3, and so on. So you don't need to do anything else. You already have that array built for you. Okay? So our right-hand side is simply B is minus delta x squared, so delta x times delta x, times S over K, times source at x over K. Source at x is a NumPy array of the same size of n points, right? This is a scalar, a single value, single value, single value, but the result is going to be an array of the correct size. It's going to have 5 entries in it. B is going to have n entries in it. If you're in doubt, print it out. So print B. This is what I do every step of the way. I don't move one line before making sure that I got it right. And I ask these questions, sanity checks. What's the size of the array? Does it have the right entries? What am I doing here? Does it make sense? If you do that every step, your code will just work miraculously. But because you're error checking every step of the way. So if I print B, it's going to have 5 values in it because I have 5 points. 1, 2, 3, 4, 5. And they contain minus delta x squared times source over K. Okay? We still need to fix the values in the right-hand side because the first value is t left and the last value is t right. Okay? So let's do that. B0 is t left, and B minus 1 is t right. And when I print it indeed, I get 300 for the first entry, which is t left, and 500, which is t right, and everywhere else is whatever the heating thing wants to do. Okay? Now I'm going to go back and put some more points because 5 points is ridiculous. So let's put 100. Okay? We have a nice clean thing here. Okay? Source term B, I don't need to print B. We're done. So now we can solve the system of equations. Solve for what? What are we solving for? The T's. What are the T's? Temperatures, yeah. What are we solving for? The dolphins, the elephants, the dinosaurs, the temperature along the rod. We're finding the values of the temperature along the rod. This is like incredible. Now you don't have like one temperature on the rod. You can find the T value at each point only knowing the boundary points and the heating source. It just blows my mind. Differential equations are amazing, and linear systems too, and numerical methods and all of that. Okay, so T, or my solution, or tsol solution, is mp.linalgebra.solve. What do we put here? What do we put here? A comma B, right? This is solving, taking a coefficient matrix and a right-hand side. Okay, you solve it. Well, what do you do? What do you do? You can print it out, but it's better to plot it out because visualizing things is a picture is worth 1,000 printouts. Okay. Okay. plt.plot. I want to plot the temperature along the rod. So T versus X, right? So I put X first and T solution. I'm going to add a grid because I really like grids. And drum roll, please. Woo! What are we looking at? It's like nobody was excited about this. This is exciting, guys. Okay. The y-axis is the temperature in Kelvin. Okay? Temperature in Kelvin. At every point along the rod. So the x-axis goes from 0 to 1, describes the location on the rod. You're starting from the left boundary all the way to the right boundary. Okay. I don't have an analytical solution. I don't have anything to compare to. Does this solution make sense? Why? Does this solution make sense? If yes, you have to back your answer. If not, you have to back your answer. You cannot make bold claims, without evidence. Does this plot make sense? Yes or no? Okay, who says yes? Okay, so it's like counting the no's. So everyone else says it doesn't make sense. Okay, why it doesn't make sense?
I want to make an assumption here, but assuming that you're putting heat onto this metal, I guess, in the middle, like the temperature should increase, reach a point, and then decrease linearly.
Okay, that's excellent critical thinking. Okay, but what makes you? Where did we put the heating source?
I thought in the middle.
Ah, let's go and look. So let's put it in the middle. Let's see. Let's put it in the middle. I wanna take this and run with it. So let's go L over 2, right? That's the middle. Okay. So let's run this again. Okay. So where's the middle? Is right here, right? It kind of starts peaking at the middle, right? Yeah, it does peak sort of at the middle. It's not exactly at the middle because there's other things going on. But without knowing heat transfer, it looks okay. Because of heat transfer, it's not going to peak exactly at the middle because heat is going to dissipate and move away, especially that there's a lower temperature on this side. But it does peak, right? So that's the point that you need to take there, that it's peaking where I'm kind of wanting it to be. So here's how I'm testing this. If I change the peak location, does the temperature peak change accordingly? Yes, and it does. So if I go to L over 3, so let's go to L over 3. That should make the peak closer to 1 over 3, right? Which is kind of like over here, right? Well, it's not peaking in this case, right? It's not peaking because this temperature turns out to be much higher than how much heating is being put in here. So what if we put more heat? Then you're going to see it peak. Okay? Now, because I know the heat transfer mechanism, I can understand that, right? But that's a great jump. So once you know heat transfer, you'll be able to interpret these things. But what other things can we say about this plot to at least see if it kind of makes sense or not? We checked at least that there's something going on where the heating source is located. Okay, so if I were to make, I'll go back to the heating source. If I were to make both temperatures equal here, you're going to get the peak exactly where you want it to be. It's because of that temperature. There's heat coming in from the right and heat leaving on the left. That's what's going on here. But, okay. But what other thing can I say? What do I know about the boundaries? Am I at least recovering the boundary values? 300 and 300 or 300 and 500? It looks like it. So that gives me confidence that, so if I put T right at 500, or T left at 500, let's say, and I change it, it's changing. Look, it's starting at 500, doing something where the peak is, and it's going down to 300, exactly as I expected. So I'm doing something right. Okay, at least I'm doing something right in this system. Now, indeed, this solution is correct. It was verified with an analytical solution, etc. And I trust this system, so it is giving me the right solution. But in the absence of that, how do you do the sanity check? You ask these questions. What your colleague asked, like, is the temperature peaking where the heat source is? Well, it's a little harder to answer that question without knowing too much heat transfer. But if the temperatures are fixed and the heating is going to cause an increase in temperature, you bet it's going to get there. It's going to make that temperature peak exactly there. Okay, now there's another test that we could do as we think about this. Now, notice that this is so easy to play with. I can go and ask you now, explore how the temperature changes for different materials. What does different materials mean? It means different K values. Is the material going to be very conductive or not conductive at all? Okay, so is K approaching 0 or infinity? You can do that very quickly with a change of a number. Put more points. Okay, let's go to, should we go to 1,000 points? We can go to 1,000 points. Okay, or 10,000 points. Okay, 10,000 points. I don't need this here. It's going to take a minute to solve it because now it's 10,000 squared, the matrix size, but it does solve it, and I didn't need to change a thing. All I need to change was n. but I have way more precision over here. Okay? Let's go back to 100 just to get speedy calculations. So I want to focus on the physics now. Okay. So let's play around with K. I said K is the heat transfer coefficient. If K is large, then the material conducts heat very efficiently. Okay? Very quickly. It gets hot really quickly. If you change the temperature 1 point, it's going to spread very quickly, or it passes heat along very quickly. If K is small, then heat is barely going to make it through. Okay? It's going to resist heat significantly. All right? So let's see what happens. Let's start what? With large values of K? Okay, so let's start with large values of K. First, what do you think is going to happen if K is very large? Yes, let's get some answers.
Where it starts at 500, it'll extend a little further to the right until it peaks and drops.
Okay. What do you think? If K is large, remember, K is large means the heat is going to dissipate very quickly. So don't forget about the peak. So if you're adding from the source, if you're adding heat from the source, what's happening? Are we running out of time? Like everybody's packing. Oh, we're already out of time. Okay.